Lesson 6-4, Solve Inequalities using addition or subtraction. In this lesson, we're going to learn how to solve an inequality instead of an equation using the same types of properties that we did when you solved a one-step equation before in, let's say, 6th grade. Okay, so these are a little bit more simple than the two-step equations you've been solving, but they involve an inequality, which means we don't have an equal sign anymore. We're going to be using our inequality signs, such as less than or equal, greater than, and greater than or equal. Also in this lesson, we're going to spend some time talking about the different wording in a question that would indicate when you have an inequality as opposed to an equation. First, let's take a look at the explain it question. Selena and Martin are waiting at the bus stop. The number lines show the possible wait times in minutes t for Selena and Martin. If you take a look at the two number lines, let's look first at Selena's number line, you notice that there is not just one solution. Instead, there is a dot at the 15, and it is shaded going to the left, which indicates other values that are also part of that solution. So the first thing that we need to do is be able to interpret what Selena has as a possible wait time. The first thing that we look for is where is the dot on the number line, because that indicates our starting point. In Selena's case, it starts at the 15, which means 15 minutes could be one of her possible wait times. But when you look at that number line, what other numbers also could be part of Selena's wait time? Well, if you consider the direction of the arrow and the shading on that number line, it travels to the left. So other numbers that are included would be numbers like 14 or 11 or even 5, which doesn't show up on the number line, but certainly if that arrow keeps on going to the left, you would run into that number. It also includes any number between those whole numbers because there is shading also between the whole numbers. So Selena's wait time could best be described as anything that is less than or equal to 15. Now let's take a look at Martin's possible wait times. Martin's possible wait times, this time you also see that there's a dot at the number 15, but this dot looks different. This dot is an open circle. It's not filled in, but there is still shading, but this time going to the right. So when I look at Martin and I consider what possible answers could be his wait time, I'm looking at everything to the right of 15, 16, 19, 25, and so on. But because the circle is not filled in at 15, that means 15 is not included as part of the solution. So Martin's wait times are actually greater than 15, but do not include 15 as a possible answer. So now let's take a look at how we can talk about these and compare them. The question actually says, who anticipates a longer wait? Well, in this case, it looks like Martin is the one that anticipates a longer wait because his possible wait times begin at numbers greater than 15, whereas Selena starts at 15, but her numbers get smaller. So the second question here says, if Selena and Martin both wait 10 minutes for the bus, whose possible wait time was closer to his or her actual wait time? So if 10 minutes is the actual wait time, who was closer? Well, if you take a look at Selena, 15 was a part of her solution. So 15 take away 10 means that she was 5 minutes away from her actual wait time and her possible wait times. And because it was getting smaller and going towards the 10, 5 would be the biggest amount of minutes away that she could possibly be there. If you look at Martin's possible wait time, he starts at 15, but his values were actually getting bigger. So even though Martin begins at 15 and we're 5 away from that 10-minute mark, notice that Martin's numbers are getting bigger while Selena's numbers are getting smaller. So Selena is actually going to be closer to that 10-minute mark. Now let's take a look at example 1. On the airline that Raul is using, the weight limit for both suitcases combined is 50 pounds. How much can Raul's second bag weigh without going over the limit? Well, the first thing that you have to do is you have to notice that the weight limit is 50 pounds for both of them. So combined, it can't be over 50 pounds. But one of the bags is already labeled at 38 pounds, so we don't know the weight of the second bag. But we can guess the weight of the second bag by solving an inequality. To write the inequality to represent the situation, we have to consider the first bag at 38 pounds, the second bag that we don't know, so that's the one that they've labeled P, and that has to be less than or equal to the baggage weight limit, which is 50 pounds. So this symbol here is the less than or equal to symbol. So we're going to actually solve this inequality just like you would an equation. You're going to use those inverse relationships between addition and subtraction to isolate the variable and get it by itself. We call this property the subtraction property of inequality, but it works just like the subtraction property of equality in an equation. You're going to do the same thing to both sides of that inequality, and when you do that, you get, instead of a single value for the variable, you get a range of values. So to use a number line to graph that to show all the possible weights that could be that second bag, you have to graph the inequality P is less than or equal to 12. So what I see here on the number line is it tells me that the second bag can weigh at most 12 pounds. It can't be over 12 pounds, or their combined weight would be over the 50-pound limit. But the second bag could also weigh less than 12 pounds. So when we graph the solution, 12 is the maximum number. So we fill in that circle because 12 is a part of the answer. And then we color going to the left to show that other values that are less than 12 would also work to make that combined weight limit smaller than the 50 pounds. So Raul's second bag must weigh 12 pounds or less to avoid going over the weight limit for both suitcases combined. Now let's take a look at two terms that appear quite often in our work with inequalities. The first term is the term at most. What at most means is that the number itself is the largest that it could possibly be. So the number is the largest, but it could be less. When you think about the term at least, that means the number is the smallest that it could possibly be, but it could actually be more. So if I were to say to you something like, I have at least $10 in my wallet, then that means I could have more than $10, but 10 would be the smallest amount that I have. If I say I have at most $20 in my wallet, then that would mean 20 is the most amount that I could have, but it could actually be less than that. So consider those two terms as you continue your work through the problems. Now complete the try it, at least this first step right here. And the first step is to complete the inequality. Then come back and we'll work through it together. All right, so in this problem, we see that Kyoko has completed 26 hours of community service, and her goal is to complete at least 90. So what that means is 90 or more. So 90 would be the smallest amount that she would complete, but we do want to consider that she may do more than 90 hours. So when we set up our inequality, we want H, the number of hours that she needs, plus the 26 that she's already completed, to be greater than or equal to 90. So looking back across here at our other notes, at least means that we are going to be using a greater than or equal to symbol, while at most means that we are going to be using a less than or equal to symbol. So consider those symbols when you see those words. Now we need to solve this. To solve this inequality, you're going to do the exact same steps that you would do if you had an equation. So ignore the inequality symbol for a minute and just go ahead and complete the solving process by taking away the 26 from both sides. In this case, H is greater than or equal to whatever 90 take away 26 is, which I believe is 64. Since H can be greater than or equal to 64, then when we place this on your number line, you're going to put a solid dot at the 64, and then you're going to color to the right, because we want 64 to be the smallest number, but we know it could be greater than that. And we color all the way to the end, and we make sure that we put an arrow at the end to indicate that those solutions go on in that direction. Now let's take a look at example 2. This time we're going to solve inequalities that involve subtraction. So the weather forecast predicted that the evening temperature could get as low as negative 12.5 degrees. Between the afternoon and evening, the temperature dropped by 7 5/10 degrees, which was consistent with the forecast. What could the afternoon temperature T have been? So we're going to first represent the situation with an inequality and then solve it like we would an equation to find out what that afternoon temperature could have been. So when we set up the problem, we start with the afternoon temperature, which is the T. We're going to subtract the 7 5/10 degrees, because that's how much the temperature dropped. And then it says it got as low as negative 12 5/10 degrees, which means this is the lowest amount, okay? So what you see here in the forecast is the lowest possible temperature. So what does that mean? It means that it could have been greater than a negative 12.5 degrees, but 12.5 degrees, negative 12.5 degrees rather, would be the lowest possible temperature from that forecast. So when we have the equation here, we know that the greater than or equal to sign goes there because negative 12 5/10 is the lowest that it would possibly go. It could go higher than that, so we need the greater than sign in there. Then as we solve an equation, we are going to do the same thing to both sides, which is to add 7 5/10, which is what they did right here in this step. They used the addition property of inequality, which is just like the addition property of equality, and they did the same thing on both sides. Now we know that T has to be greater than a negative 5. Then we have to go over here to the graph and graph that. When it says that T is greater than or equal to negative 5, that means it could have been negative 5 degrees. So there's a solid circle there to indicate that negative 5 is one of the possible answers. But greater than negative 5 means go to the right and then color in an arrow at the end to indicate that those values could have gotten warmer than negative 5 degrees. Now I want you to take a look at the triad. The triad is a similar problem that asks you to set up an inequality involving subtraction. So I want you to pause the video, see if you can get it set up first, and then come back and check your setup, and we'll go on and try to solve it and graph it. All right, so when I take a look at the wording here, we know that the speed limit drops to 15 miles per hour around the curve, And it also tells us later in the problem that Mr. Gerard never drives above the speed limit. So in other words, his speed is going to be less than or equal to the speed limit of 15. What we also know is that he slows down by 10 miles an hour to go around that curve. So the slowing down process is why we're subtracting 10. I chose S as the variable to represent Mr. Gerard's speed before the curve. So his speed before the curve minus 10 miles an hour, so that slowing down of 10 is still going to be less than or equal to the 15 mile an hour speed limit. Okay, so let's go ahead and take a look at the solving process. I want you to use the addition property of inequality and solve this just like you would an equation. So pause the video and come back and check your answer and see if you solved it correctly. Now we know that Mr. Gerard could have been going up to 25 miles an hour before the curve in order for him to slow down 10 miles an hour and still be at or under the speed limit of 15. Now we have to graph that. So the first thing we do is we sketch a number line. And the easiest thing to do is to take the number that is a part of your solution, 25, and just stick that on the number line. Perhaps put number before it and a number after it, just so that you can see the range of numbers that would be included. The next thing that you do is you put a dot where you have the solution begin. So in this case, the solution begins at 25. Now, that circle needs to be filled in to represent that 25 could be the speed limit, or the speed that Mr. Gerard was going before he slowed down and got to that curve. And what we know is that his speed could not have been over 25 miles an hour, or he would have been over the speed limit around the curve. So we're going to shade going to the left because it's a less than or equal to symbol. Now I want you to complete the triad that goes with example 3. So you do have fractions, you will need a common denominator. See if you can solve that and come back and check your answer and your solution graphed on a number line. Okay, go ahead and check your answer to the triad that goes with example 3. See me if you have any questions. And when you're okay with this, I want you to go on to the next video called Accelerated Lesson 6-4 Practice Work. And you're going to try some questions on your own, and then we'll work together on some others, and you'll be able to check your answers on those as well.